Good afternoon, ladies and gentlemen. Just need to correct something. I said this morning, I thought it was the sum of 7. It's in fact 7 or more. So Sam actually is correct. Where's Sam? So if you want to come along and receive your fiver, come along. So from Richard. And in fact, Haider actually got the right answer as well because he thought it was sum of 7. So there's another fiver. Very costly, very. And there's another fiver actually now here in this presentation. So ridiculous, isn't it? Very expensive, yes. Okay, so this is completely different. This has nothing to do with traffic. You'll be relieved to know. This is actually a nice project. I did this 16 years ago, actually, or 17 years ago. So that's 2003. So I'll talk about, there was an accident. I guess a lot of you are familiar with runaway escalators. Very, very, very prominent, very widespread. Strangely, I don't know, where's David Cooper? Very strange that I don't know, I'm going to use the word. I think we're a bit complacent. There are lots of runaway escalators. I don't know why. Anyway, a closer look at escalator braking, escalator types, tools, mathematical model, conclusions, recommendations. Anyway, this is from, I think this is 4-lane ends. Anyone familiar with the Newcastle Metro? Is this 4-lane ends?
Looks like 4-lane ends, right?
No? Yeah. So there's the other fiver. So there's one odd photograph in this presentation. If you can spot it, and it's quite subtle, actually, this is like the have I got news for you. If you set it, there's another fiver. Unfortunately, I've only got £10 notes, so you have to give me a fiver back. Okay, so I got a call like David Cooper. It was from the Tyne & Wear Metro Nexus. And there had been an accident. There had been an incident at Escalator Monument. End of a match at St. James's Park. They close for crowd control purposes. They would close the station. The St. James's Park station would be closed. So all of the football fans will have to walk to Monument. Large numbers of people going down the escalator. Someone either panicked or a safety device tripped. So what should have happened is the safety device tripped, it triggered the brake. The brake is spring applied, so even if there's no electricity, it would stop, and the escalator should have stopped. What happened actually is speeded up. As soon as someone hit the button, the stop button is speeded up. And then it increased in speed, and then it threw people at the bottom. Now, as everyone had got off, it slowed down by friction because now it's fully balanced. And so it gained excessive speed, 2 meters a second or more than 2 meters per second. Did the investigation, finished all of that. That's how it started. Now, the follow-up. So as a conscientious management of the Metro, a guy, David Brown, I think at the time, I don't know if he's still there, he felt they had to do something. I had to follow this up. So, and to their credit, they decided to do a full review of the whole maintenance, adjustment, setup, and so on. And my task was not just to do the report and go away, is to work through with them step by step, until we get everything set up. So all the tests done, all the training, and so on. Very nice project, the best part of a year. And that's where the concept of weightless weight testing came up. So runaway escalators, the first time I saw this was 1989. So this was the CN Tower, an incident at CN Tower. Runaway situations, quite a scary runaway situation. Brakes not adjusted. So 9 children were taken to the hospital after being in a human pile-up. Now this is the critical word is after the emergency stopped. The motor wasn't doing anything. The motor had switched off. Electrically, the thing was disconnected. After someone hit the emergency stop button, it speeded up. Some of you might have seen these slides before. I started actually tracking all of the incidents of runaway escalators. So there was one at Oxford Circus, escalator number 4, Nashville International Airport. This is one of these. And one of them was up, and it actually reversed and came down, because gravity will pull it downwards. So even if it was an up escalator, it will reverse and go down. Waterloo, that's Waterloo, London Underground. Anaheim, California, baseball fans, 2002, 15 passengers with minor injuries. Now, obviously, the nature of the injuries, I wouldn't say minor, but you're not going to get amputations or serious entrapments. It's mainly people piling on top of each other at the bottom of the escalator, which can be serious. I'm not saying, but it's a minor injury. There was one in China recently. Dave, I'm sure Dave can tell us more about it. I didn't record it. Coors Field Stadium. That one, Jim Fortune, I think, was investigating. I don't know what the outcome of the investigation was. All of those are runaway escalators. So when I use the word complacent, I think I'm justified in using it. People become very defensive if you say the brakes are not adjusted. Raffles City Centre, Singapore. That's one in China, Shanghai, and 38 people injured, none of them severely. Okay, so let's have a closer look at escalator brake testing. So we talk about an operational brake, an auxiliary brake, brake requirements. These are all set out in the standards, different standards. I don't know if ASME has changed, Rory. Still 0.91 meters per second square. Now, the traditional way that it's done to test the brakes is people will basically go through the brute force method. Put weights, these are 50-pound weights. You have an army of people, like 20, 30 strong men. They'll carry those, put them on the steps, start with 25%, run it down, check the stopping distance with a bucket and a flap. 50%, 75% until they get to 100%. Adjust the brakes, check them, make sure that it's stopping within the distance, and then take it off. It's a very costly exercise. It takes a night or 2 nights. It could cost up to £10,000. That's why people are reluctant, or companies are reluctant, to do that full test. This is a very good slide because it tells us so much. This takes probably something like 3-4 hours to compile. Test, measure, and compile. But it tells you so much about this is one of the images that tells 1,000 words. So we press the stop switch. So that's when the instruction was given for the escalator to stop. This axis is speed, that's time. So what we're saying is it was running at around 0.65 meters per second. From the minute we gave the instruction to stop until something started happening is 344 milliseconds. That's very important. Okay, you really need that level of detail to understand what's happening. And the only way to do it is to register what time you press the stop switch. Then, this is a frictional stop. Frictional stop means the escalator is just stopping under its own friction. So, and you can see there's no difference there, which means this is a mechanical delay. It means the brake is still moving and it still hasn't touched, the pads still haven't touched the disc or the drum. And that's the further delay of 359 milliseconds. So we're saying it's around, on this escalator, I'm not saying every escalator, but that tells us a lot about what's happening with an escalator. Now you can see this is deviating from this. So we're starting to get some braking effort, and the braking effort actually maximizes somewhere down here. So that's showing us what, and we've come to a final stop now. This is also very interesting. This is telling us what's happening at different loads. So when we have no load on the escalator, obviously, logic says that we have the sharpest stop, the highest deceleration. 50%, 75% load, and 100% load. What you will also notice, very important, is this. It's accelerating. It's got nothing to stop it. So we've taken away everything, the motor, which is an electrical brake. So you would see that the thing has started accelerating. And you can hear it in the machine room. You will hear that noise, that classical noise. It's speeding up, which is a very terrifying moment. Because if it doesn't start coming down again, it will crash at the bottom. And then comes down here at the end. So that's actually very useful, because with all of this data, you can then start understanding what's happening and how to tackle and how to build a model. Another one, electrical delay, mechanical delay. So the decision was they had 4 types of escalators. They have 32 escalators in their fleet, all of them Orenstein and Koppel, O&K escalators from Dortmund or Düsseldorf? Dortmund. Installed in the 80s, 82 I think, all 32 types. So the plan was we'll do a full weight test on each one of the 4. So we'll pick 4 escalators, do the analysis, then we have the data, and then predict the performance of every other escalator from those. And that's what I've called the weightless weight test. So they had HD M10s, heavy duty M10 escalators, and that's their brake. Very nice to adjust and so on. There's the disc. You can see the pads there. And there's a spring. And you compress the spring, you get more torque. You undo it, you get less torque. Compact, two motors, and that's the solenoid. HDMS, I think. And that has something very interesting, which is a band brake. And a band brake works very much like an oil filter spanner. It only works in one direction. It doesn't work in the other direction. So it only works in the down direction, which makes sense. If you don't know that, you'll spend a lot of time trying to adjust it in the up direction, which we did. But then I was so happy when I found this to illustrate the concept. So. RTV HD, that's, and the spring is inside here. And you need to get a special type of C-spanner to tighten that up. Okay, anyway, so we did a weight test on each one of those. That was the plan. So a weight test, costly, expensive, but at least we could get the data from that and then not need to do a weight test again. So we used a good old PMT unit. Those are familiar with that. Now this is the important point. We record exactly when the stop switch was pushed. There's a small handheld pendant in there, which has a small switch inside. So as soon as you press it, you know that that's the moment at which the instruction was given for the escalator. There's a lot of controversy about the handrail and whether you really should use the handrail or you should use the step band. It was much more convenient to use the handrail. Download the data, analyze it, extract all the results from there, maximum deceleration, stopping distance, and so on. Weight test, 4 weight tests, so 120 kilograms per step. And then central station, monument southwest. A monument southwest, I can't remember the S, I think it's southwest. Sets of curves generated. Nice curves, they actually follow what you would expect. So you would see at different loads, you're getting different slopes. Up and down here, for some reason we found some difference between up and down. At central station, monument, north-south, and these are quite nice as well, nice curves in there. So got all the data, all of it summarized on here. And from that, now that you have all of that data, you can develop a mathematical model, which is great because now you have all of that information put into a model, all of the set of equations. And now you can predict the stopping distance, you can predict the deceleration, and incorporate all of this information. Electrical delay. What's the mechanical delay for this type of machine? What's the mechanical delay? What's the linear speed, acceleration during? And that's a simplification, but it's actually a nice simplification. Because what this is saying is, there's a delay there. Remember that during that delay, it's still running at rated speed. So all of that distance, it's covering all of that distance. It accelerates. As soon as you hit this switch, it starts accelerating. Then the brake starts working. So you need that area, and this area. And you've predicted the stopping distance. Or you can predict the stopping distance without having to do. Now, what's nice about that, we did all of that. Every single escalator was done, adjusted, tested. A nice sheet was produced, which I'll show you in now. And then there was the recommendation. What do we do now? So every escalator would be checked every 6 months without weights. It's not feasible to repeat a weight test every 6 months. So the whole idea of this now is we just do a quick no-load test every 6 months on every escalator, record the results, compare them to the model, and then decide whether there's any cause for concern or not. At 6 monthly check, at least it tells us that we don't have a runaway situation. Compare this now to doing a weight test every 10 years and assuming that you have a false sense of security because 10 years ago or every 10 years I'm doing a weight test that the escalator has not changed during the 10 years. This is much safer. The first one is much safer. Because if to do a weight test, it's very, very costly. You can't do it every day. Minor modifications are being carried out. If you carry out minor modifications, there is a procedure for doing that. Let's conclude the conclusion recommendations. So weight test carried out on 4 escalators each type to understand the behavior. Light slip test. The light slip test is a no-load test. You just stop the escalator with no load and take measurements. All results were tabulated. That's a nice card. So a card was produced. And the maintenance guys would I've just removed the names from there, the names of the stations. And what it distinguishes, it tells the user or tells the maintainer what value he should expect to comply with EN 115, but more importantly, what value is actually dangerous and should withdraw the machine from service. So 0.41 is saying if this machine tries to stop, it will not stop, it will speed up. A value around 0.68 or better means you're complying with EN 115. So you could say, I will withdraw a machine from service if it's that value, and I can raise a concern to be done within a week or 2 weeks, for example, which is reasonable. Full training was done for all of the staff. And 6 monthly light slip tests were carried out, compiled into a spreadsheet. You can reduce the frequency then if you feel that things are okay. There was a lot of discussion about what to do with the brake. There's, for those of you familiar, operational brake is the brake that works every stop. The auxiliary brake might or might not, depending on the configuration. It's very much like a backup brake, and it operates under certain conditions. These were the values we were looking sort of for 0.7 meters per second square. 3-year auxiliary. We did a frictional test. The frictional test gives you an idea about the status of the machine. So if it's taking a long, long time to stop under friction, it means it's a nice machine, there are no problems. If it's starting to take less time stopping on friction, then that could point the maintainer into the direction of doing something about it. There was a problem of oil contamination, so that's one of the practical issues that you come up against. There's no point in adjusting and replacing and so on if you still have oil contamination, and it just takes the brake out completely. Finish on something nice, interesting, so nice piece of engineering. This is the footbridge, the Millennium footbridge, which I started with. And it has a clever way of letting the ships pass. So it just has to turn by 45 degrees. And that's it at night. Thank you very much for your attention.